Today we're going to look at the Maclaurin polynomial of fourth degree for f of x equals 1 over x. So we're going to start with f of x, and that is 1 minus x to the negative 1. And if we evaluate this at 0, we get, well, it's just going to be 1. F prime of x is negative 1 will go down here, but then we'll multiply by negative 1, making it just 1. So this is 1 minus x to the negative 2. If we evaluate that, we get 1 again at 0. Second derivative is going to be 2 times 1 minus x to the negative 3. And if we evaluate that, we get 2. Evaluate this at 0, of course. The third derivative is going to be negative 6, but we're going to multiply by negative 1 again from the chain rule on the inside. So we get 6 times 1 minus x to the negative 4. Evaluate at 0 will be 6. And finally, the fourth derivative will be 24 times 1 minus x, and evaluated at 0 will be 24. Now, let's take a look at these numbers. They happen to be equal to 0 factorial. This is 1 factorial. This is 2 factorial, 3 factorial, and 4 factorial. If we keep going, whoops, I need negative 5 there. We'll multiply by 5, then we'll multiply by 6, and we'll multiply by 7. So you just keep getting the factorials. So the Maclaurin polynomial of fourth degree is equal to 1 plus 1 times x plus 2 factorial times x squared over 2 factorial plus 3 factorial x to the third over 3 factorial, and finally plus 4 factorial x to the fourth over 4 factorial, which hopefully you can see that this is going to simplify to 1 plus x squared plus x to the third plus x to the fourth. Now if we take a look at the graph of this, let's see if I can bring it up. Oh, an axis violation? What does that mean? Oh, there it is. I don't know why it gave me that the first time. I've plugged in these values. You can actually turn some functions on and off just by hitting on the equal sign. So if we graph 1 over 1 minus x and we graph the fourth degree Maclaurin polynomial for it, we get there's the 1 over 1 minus x. You can see the asymptote, and here comes the approximation, and you can see that we can't allow x to be 1 because we'll have a vertical asymptote there, and this approximation gets bad. Right here is negative 1. So this is a pretty good approximation between negative 1 and 1. And we've actually looked at, let's see what I graph. I went to the 9th degree. Let's turn the second one off, and we'll turn the third one on. And maybe we'll make this one the dark one, the thicker line. If we graph these, there's the 1 over 1 minus x, and here comes the 9th degree. It should come from the bottom, and it's going to follow the curve very closely. But this still kind of breaks down at negative 1, and it starts breaking down really at 1. So this converges between negative 1 and 1. If we look back at this function, let me click back on this. This is really a power series is what this is called. Well, let's go back and say that, well, really what it is, it's a geometric series. The a being 1, and we're multiplying by x every time. So we could write this with sigma notation, n equals 0 to infinity of just x to the n, where the a is 1. And of course, when we have a geometric series, well, let's write the 1 in for right now. When we have a geometric series, we said that it converges, the sum converges to 1 over 1 minus r, and in this case what we're multiplying each time is the ratio is x. Well, we said that this is good as long as the absolute value of x was less than 1. Or we also said that it has to be x has to be between negative 1 and 1. Well, this is all the characteristics of a geometric series. Well, we call this right here, that is now, we have a special term, and I kind of alluded to it before, accidentally really. This is called a power series. And a power series is 1 plus x squared plus x to the third plus x to the fourth, keep going, plus x to the nth. And it can be written as sigma notation, n equals 0 to infinity of x to the n. Well, we have a power series, and if it's centered at 0, f of x will equal n equal the sum of n equals 0 to infinity of a sub n x to the nth. So we could have some constant out here, and it's still a power series. This is equal to a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x to the third, and so on. If a polynomial is in the form or represented by a series in this form centered at 0, this is called a power series. If we have a polynomial represented by this series, this is a power series centered at x equals c. So it could be 0, but it could be any other number. So we have f of x equals summation n equals 0 to infinity of a sub n x minus c to the n equals, and you can see that rather than just having x's here, we'll have x minus, whoops, not a 3 here, but a c. Got carried away with the 3's. Let's investigate this power series and its characteristics, that some of which I've mentioned already. We have summation n equals 0 to infinity of x to the n, and once again, this is a geometric series where in this case a equals 1, and the r, the ratio that we're multiplying by, is x. And it does have the characteristic that the absolute value of x has to be less than 1. What that tells us is that x has to be between negative 1 and 1, just by the definition of absolute value. But really what that tells us by looking at the graph is that's where the series converges. And it's really where we have good estimations of the polynomial. If we get beyond negative 1 or 1, then we're not going to have very good values for the estimation at all. Now this is called the interval of convergence. And if we were to graph this, if just go back to old Algebra 1, graphing inequalities, we'd have negative 1 to 1, and I suppose 0 would be in the middle right here, and we would graph this with open dots on each end. But we also have another terminology. If we go right down the middle and go to one side, this is a length of 1, so 1 is called the radius of convergence. So there's just some terminology for us. This is a geometric series. It expands out to the power series. We have an interval of convergence, and when we graph it and split it right down the middle, the radius of convergence ends up being 1. Another little tidbit of information is that this series, the sum, converges to 1 over 1 minus x, which really comes from that little formula we have, which is a over 1 minus r. Here we have an example. The example says find the interval of convergence and the function of x represented by the geometric series. Here's our example. We have sigma n equals 0 to infinity of 3 times x minus 1 over 2 to the nth power. This is a geometric series. We have our a as 3, and we have our r as x minus 1 over 2. So if we want to find the interval of convergence, we know that the absolute value of r is going to be less than 1, and in this case our r is x minus 1 over 2. That has to be less than 1. Well, now we can write, just by the definition of absolute value, that this r has to be between negative 1 and 1. So we multiply by 2 and we add 1. So we have negative 1 is less than x is less than 3. Now there's our interval of convergence. So the interval is negative 1 to 3, not including those points. Well, if we were to take the old-fashioned, put this on a number line, here's negative 1 and here's 3, and we'd have 0, 1, 2. We have to find the halfway point, cut it down the middle, and here is our radius of convergence. If we were asked that, radius of convergence would be 2. It would be 2 units. So this is our interval of convergence, and this would be our radius of convergence. Now we want to find the function of x represented by this geometric series, and we know that just by this little formula that this converges to a sum of a. In this case, a is 3 over 1 minus the r, which is x minus 1 over 2. Now if we multiply everybody by 2, we get 6 over 2 minus x plus 1. The 2's will cancel. If we distribute the negative, that becomes positive, of course. So the function of x represented by the geometric series is 6 over 3 minus x.